Hey everyone, this is Miss Weaver, and this is the first video for section 10.3. Alright, so the good news is we've actually covered a lot of the basics in sections 10.1 and 10.2 for hypothesis testing, and so there's really only one difference with testing a hypothesis for a mean, and that's just the actual test that we use, which of course our calculators are going to help us with. So in this section, we're really just going to look at several examples of testing a hypotheses for a population mean, and we're also going to talk a little bit more about significance. So in section 10.2, we talked about statistical significance. And in this section, we're going to talk about practical significance. But we'll do that in another video. So that'll probably be in one of our last videos that we look at for this section. So let's start off with just kind of a quick review of what's the same. So we are still going to write our null and alternative hypotheses. So our null hypothesis, before we were using p, so maybe p equals 0.5. Now for this section, we're going to say mu, and it will be whatever we might be looking at. If we're looking at the heights of young women between 18 and 24, then maybe the mean height is 64.5 inches. So that would be our population mean. So we still have our null hypothesis, we still have our alternative hypothesis. And so remember, this can be any of our three absolute inequality symbols. So we don't want to have anything that includes equality at all. So I'm not going to have a less than or equal. I'm not going to have a greater than or equal. I'm definitely not going to have an equal because that's in my null hypothesis. But I'm going to either have greater than, or, again, so that might be, 10.2, we dealt with proportions. We might have a less than. Or we might just say we don't know if it's the same. So we think that maybe if we stick with the young women, heights of young women, then maybe we just think that it's changed since we got this number. So those stay the same. We still have a significance level. That is alpha, and it's going to be something like perhaps 0.01, 0.05, maybe even smaller, 0.001 in some cases. I've seen some problems, and especially reading some journal articles where they've said the p-value is less than 0.001, so less than 10% of a percent, so very small. So significance level is going to stay the same, and then our decision. So remember, we had two decisions we could make. We could reject the null as long as our p-value is small, or we could, I'm not going to be able to close that parentheses. I've got stuff in the way. Oh well. And then we could fail to reject. The null if our p-value is not small or not unusual. Oops. So that's what those are some of the things that are the same. And then our conclusion is really going to be basically the same as well. there is sufficient or insufficient evidence at our significance level to suggest, and then we put our context in. So the only thing that's different is getting that p-value. So let's see, where can I put conclusion? I'll just write down here. So we'll talk about that as well. So we've got all of this stuff that's the same. The only thing that's different is coming up with our p-value. All right, so that one thing that's different, coming up with that p-value, how do we do it? So how do we get a p-value when testing for a mean? Well, let's think back first to what we did in section 10.2. So in section 10.2, we used a one prop z-test. And remember that prop was there to help us remember that prop for proportion. And we had also used, way back in chapter 9, in section 9.1, we used the one prop z int to find the confidence interval for a proportion, so that they have that same naming scheme. So one prop z interval or test. Well, luckily, we're going to have the same connection for doing our hypothesis test for a mean. We used the t interval in section 9.2 in order to come up with our confidence interval, and so now we're going to use the t-test to test our hypothesis for a mean. All right, so our t-test we can get to just like we did for our one prop z-test and our t-interval and one prop z-int, and that's by going to the stat button, over to the tests menu, and down to number 2 where it says t-test. And just like with t-interval, we actually have two options. If we have data that we put into a list, then we'll use the input data, and we'll actually just tell, you remember this tells us our null hypothesis. Oops. Is where it says mu naught equals 0 right now. That's going to be our null hypothesis. And then we want to identify our alternative hypothesis right before we click calculate. Or if we don't have data, if we don't have the list itself, but instead we've been given the mean and standard deviation and sample size, then we will switch our input to stats and we'll put those values in. So we put in our mean, standard deviation, and sample size as given, and then we can select our null and alternative hypothesis information. Of course, in both cases, once we hit calculate, that calculator will give us, remind us what our alternative hypothesis is. It will then tell us our t value, so our test statistic for the hypothesis test for a mean will be a t-score instead of a z-score. So we'll have t equals, and then we'll have our p-value, so p equals, and then it will remind us, now of course if we put this in the statistics then it's just redundant, but it will give us x bar, sx, and n for our sample. And of course, just like with our t-interval and with our one prop z-int and one prop z-test, we have conditions that we need to make sure are met before we use any of our tests. And that would be true even if we were learning various different tests that we might have. And our conditions for our t-test are very similar to what we've seen already several times. The first thing, of course, is our sample either needs to be obtained by a simple random sample, or our data needs to result from a randomized experiment. Next, we need to make sure that our sample has no outliers and comes from a population that is normally distributed, or our sample size is large, and we've been saying that n needs to be greater than or equal to 30 in order for us to assume that basically that the sample means will make a normal distribution. So that's that same idea that we had back in section 8.1. And then last but not least, our sample values need to be independent of one another or be treated as such. And again, that's just that same check that we want to do of making sure that our sample size is no more than or less than or equal to 5% of our population size. And of course, we rarely know our population size. So what we've been doing to check that in the past is actually dividing the sample size by 0.05 and making sure that it makes sense that our population size is at least that big, so that our population size is actually greater than or equal to n divided by 0.05. And of course, we don't need to memorize that second. That's just what happens when we solve. This one is much easier to keep in mind.